Vidhir V. Bharadwaj. Welcome to episode 48 of Genesis of Tomorrow. The following is going to be a conversation about gravity, gravitational waves, astrophysics, and so much more with Dr. Purnima Narayanan, a gravitational wave astrophysicist and someone who's very well versed in all these different matters. Also, folks, if you're interested in such deep science and deep tech conversations and are able to derive even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the videos and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. Want this conversation to begin with is maybe for somebody who's tuning in with not much of a scientific or formal background in the field. What is the entire story behind the entire field of gravitational waves, and why did it matter to humanity from when it began?
Okay, so why even do science? Let's start with that question. I mean, what is science? What is physics? Why even study physics in schools? And why even spend millions of rupees, dollars in doing research and not just physics and for just science or STEM? Well, the whole point of science, as I understand, is trying to understand nature. You're just trying to get, because nature is so beautifully complicated that you need all these tools and all these research and everything to be able to understand them from a human point of view. And physics especially looks at different aspects of nature, ranging from the smallest of the particles to the largest of the particles or largest of distance ranges. So when you talk about gravitational physics, it also stemmed from gravity, from the times of Galileo and Newton and Einstein and everything. So what these people were trying to do is just understand nature. Why was the apple falling down towards the ground and not just flying in some different directions? And while he was trying to understand a simple phenomena that we neglect today, he stumbled upon gravity. And then he noticed that the universe was built so beautifully that he only needed a few laws to be able to explain what happens everywhere. And then a few centuries later, we had more advanced scientists with more advanced mathematical tools and more advanced technologies. And they figured out that gravity does not work the same way as Newton had postulated, and they were trying to understand nature even deeper. So, say for example, if Newton's laws is enough to understand just our day-to-day activities and everything on a local scale, these people wanted to understand nature on a little bit of a larger scale, where Einstein came up with this theory of relativity to understand why the planets move around the sun in a certain way, or why were there errors in our GPS systems if we were to use Newton's laws of gravity. And today we are able to overcome those errors because we're using Einstein's laws of gravity. So similarly, the concept of gravitational physics, or even the field of gravitational physics, just stemmed from a basic human curiosity of trying to understand nature and trying to understand the universe. So we are in a time when the technology has become so advanced that we are even looking at something that does not emit any radiation like black holes, right? I mean, there is some different radiation that is not possible to observe with our conventional telescopes, but let's not go into that. But these are some things that is really, I mean, it bothers some people, but some people might think that it's just millions of kilometers or miles away, and why should we even bother it if it's not going to affect us in our lifetime, or if in our kids' life, or even our grandchildren's lifetime? So why even bother? But there are some people who cannot stop thinking about these things, and they just become scientists, and they try to persuade the government to invest some money just to bring up or build up science. So, gravitational physics is an opportunity that we have today to study gravity deeper, because gravity is such a normal force that we're experiencing each and every day and each and every movement of ours, that you can just neglect it in a day-to-day life. But when you really ask, what is gravity? Why does it act the way it acts? There are so many unanswered questions about it. So that is, I would say, would be the motivation why people study gravitational physics for a larger scale from a common man's perspective. And the reason why the government is spending so much money is not only to take science forward, but even the technology, and from the computational standpoint, we have so ahead of our times that these technologies can also be used for other practical applications. So the discoveries or the technological advancements that happen within gravitational physics or within these research fields are not always confined to research. Once it's tried and tested and proved, there's going to be 100 other applications to other fields. So I would say this is the reason why someone would worry about gravitational physics, or someone would be interested in something called gravitational physics.
That's honestly by far one of the more engaging and I'd say engagingly thorough responses to the question of in general why science that I've come across. But building
Thank you.
upon that, then we understood why somebody would want to figure out what gravity has got to do. What is gravity then? Like, apart from what you learn in high school, that okay, force works so and so way, there's this formula, you use it to solve a bunch of numericals, so on and so forth. Fine, high school kids can do it. Researchers at that level, what actually is going on?
So what we have, I mean, when you talk about these people like Newton, Einstein, and when you say it's a theory of gravity, right? So even though it's been tested and tried for so many years, we still call it a theory. So that means we don't know factually what gravity is. What we all have is a theory, and we can have countless number of experiments to figure out or to prove or disprove if these theories are right or wrong. So today, the theory that stands, or today, the way we understand gravity today at a higher level, is based on Einstein's theory of gravity. Although this theory is not complete, it's not complete in the sense that it's not able to explain everything that's happening in nature. It still has some limitations, but this is the long-standing proved theory of gravity, where you use a very different mathematical framework in order to understand the very simple effect of gravity. So, in Newton's way of gravity, is that you have two masses, they both have some inertial mass, and they would have some attraction force, and this force is a non-contact force, and there is some pull of attraction between these two bodies, and that's why they are attracted. So that's how Newton would explain gravity. But Einstein had this really nice visualization, which is out of the box for his time, where he imagined gravity in terms of space and time. So, first, what he does is he tries to explain just the space that we see around us and just the evolution of time from a mathematical standpoint. Once he develops that mathematical standpoint, then he introduces the effect of gravity. So the framework that we use for or we use and is widely used for studying gravity is, imagine there is this large mesh, almost like a trampoline mesh, where one axis is space XYZ and other axis is time. And that mesh is prevailing everywhere around the earth, around the sun, around us, everywhere. Now, when you have Earth on this sort of a mesh, when the because of the mass of the Earth, there's going to be a dip, right? And because of this dip, the mesh around it is going to be curved. And when you have a smaller object in this dip or this curve, its natural tendency is going to be to come closer to this larger object. Imagine you have a basketball and a trampoline, and you have a table tennis ball which is just trying to come around this. So, this curvature of this space time mesh, that he defines as gravity. So that is our understanding of gravity as of today, which we are trying to verify if it's right or wrong.
Hmm. Hmm. Then again, maybe a follow up to that would be naturally to think about how exactly does relativity, because when you again talk about Einstein, to common folks it's synonymous with these two three terms, right? So relativity, when you look at gravity, or maybe let's start with in general the concept or phenomena of forces in the pre-context of relativity in this space-time continuum as we established,
Mhm.
how exactly are these two elements, relativity as a phenomena and forces as another conceptual phenomena, are working or meshing with one another in this space-time continuum?
Yes, so we specifically use the space-time continuum to describe gravitational force. So, say for example, you want to explain a different kind of force, like a tension force, right, which is just in a string. You would not need the framework of space and time. Or if you have a different force, say for example, just a muscular force where you are in contact with something and you have to push it, you wouldn't need again the framework of this. We or Einstein developed this framework because gravity was so elusive that, and he was trying to merge electromagnetism or electromagnetic forces with gravitational forces. So it was just a simple question of why is the speed of light not changing with time? Because in Galileo's times or in Newton's times, the speed of light is just a velocity, right? So if I am in a train and I'm flashing a laser, the speed
Hmm.
of light for someone who's sitting outside should be the speed of train plus the speed of the laser, right? But Einstein proved that that's not the case, and the speed of light is constant, and blah blah. So, when he was trying to bring together these different worlds of electromagnetism and gravity, that's when he stumbled upon this genius idea of the space time framework and the idea of gravity being a manifestation of this force. So, we talk about forces. As far as I know, we use the space time concept only to explain gravitational force. We wouldn't specifically need it to explain other forces because we know the source of electromagnetic forces. They
Hmm.
are because of the electrons and the charges and so on. So this concept of curving of space-time or something being pulled was developed in order to integrate gravity within the mathematics that was developed at that point.
Hmm. Hmm. One other very, I'd say, right now, well, booming things or lenses to look at it is when you attach quantum to anything, right? So when people talk about quantum gravity, primarily again to shed some actual scientific light upon the matter, what is quantum gravity or that particular perspective? Plus, along with that, when we talk about quantumness, this very innate predisposition or intuitive understanding that you are given is that okay, the quantum effects they minimize with the macro scale, that this when the scale increases the quantum effects deplete sort of. With gravity it's sort of the opposite. When the scale increases, the effect of gravity, to say, that increases. How is then this phenomena, which is generally coincident with the micro scale, be applied to something that is generally coincident to the macro scale?
Yes, that's a great question. So quantum by itself means you're going into smaller scales, right? So just I'm just going to talk as if I'm going to talk, I mean, as if I'm talking to a layman. So imagine I have a gold earring. I'm trying to break it into pieces and I'm trying to use a microscope and go inside. I might find a gold atom. I try to dissect it more and more and more. And I try to find what is inside that gold atom. I might find a bunch of electrons and protons and neutrons. And then I try to go more and more and zoom in inside these electrons and inside these protons. I might find some fundamental particles that are making them up. So what we see today as what we are wearing and what we are seeing around us, that itself is a macro scale, right? So when you define micro scale, it's at the level of atoms and electrons and protons and so on. So the laws of physics that are used to describe such small scale particles would be classified as quantum physics. Whereas something that is used to describe something like planets and stars and galaxies and the cosmos at the larger scale would be gravity. So the question is, how would something that is used to describe such small scale combine with something that is used to describe these large scale? And the short answer to it is we don't know. There is no such theory that has been able to beautifully explain the transition from this micro scale to macro scale. And that is the whole research of quantum gravity, is to understand how gravity would behave if you go on such small scales. The disadvantage here is that when you have to go to really small scales, you need extremely high energies to bombard two electrons or bombard two protons in order to find exactly what's going on inside them. And at such high energies, it's been hard thus far to understand how gravity is behaving at that high energies,
Mm.
where high energies are related to small scales. Whereas when you talk about planets moving around the sun, or even the gravitational force between two stars, or even a supernova explosion, these are phenomena which are happening on an energy scale which is easier to apply gravity to. And this is another big reason why we study gravitational physics, is because today we have a tool to look into these really high energy explosions, like black holes colliding with each other, or even supernova explosions, and how gravity is behaving around these, which I think we'll come to at a later part, which is gravitational waves. So so this is one open-end question which we do not know. There are a number of theories which suggest that this is the solution, this is the answer to everything, this is the theory of everything, etc. But the question is, how do you believe it until you have experiments or observations to corroborate them? You
Mm.
can't. They would still remain a theory on paper. So that is the challenge that scientists find, is to how to devise these experiments where you can overlap quantum with gravity with the technology that is available to us today, and still verify if the current theories of gravity and current theories of quantum are still overlapping each other or
Mm.
agreeing with each other.
Before moving on to the gravitational waves part and maybe black hole singularity, all of that, before that, maybe I think it would benefit to talk about this duality in regard to the work, the day-to-day sort of work that you as a researcher is expected or in general find yourself doing. Because at one side there's this glamorized pop cultural reality of what a researcher looks like, what their workflow looks like. On the other hand, it's actually the reality which you must be well versed with. So again, that sort of comparison.
Mhm. Yeah, sure. So where do I start from? So life, so it has actually been my journey from being infatuated with physics or astronomy or astrophysics to understanding the reality and being disappointed with the reality, and then coming to a point to finding the balance between the fun stuff and not so fun stuff. So I started off by attending public talks, looking at these beautiful illustrations and beautiful animations on the web, and looking at these pop science movies and etc. So that's how I was infatuated with astronomy and astrophysics, because it all sounded so mysterious and just so far reaching that I just felt like if I would be able to contribute to it, it would give a sense of purpose or sense of achievement to me. And then when I started going a deeper, doing my bachelor's and master's and looking into research projects and getting my hands dirty with some actual work, that's when I realized that the work that goes behind these beautiful animations is very monotonous. It might look like sitting in front of your computer for days, spending hours of a day and spending days to get this one beautiful animation on screen. Or when you hear this large announcement, oh, the Large Hadron Collider has found something called as a God particle. That sounds so exciting and fascinating, but the kind of work that exactly goes behind that is spending time with your instruments, and it's mostly like repairing and fixing the instruments. The science is still easy to apply, but the debugging of the codes, the debugging of the softwares, repairing the equipment, so all those are the back end kind of work that go into. So when I realized that as a researcher, my work would be mostly dealing with a lot of mathematical formula or dealing with a lot of coding on a day-to-day life, debugging as much as I can, it just made me question if this is the purpose or the sense of achievement that I wanted to gain. So is this what is the relevance to all this?
Mm.
And then in the last couple years of my PhD is where I was able to find the balance and find my niche, or the point that brought me happiness is to interpret science the way I that is true to me, and to communicate that to audience, to the general audience. So what I love the most about science or astrophysics is problem solving. It could be as, I mean, even if I have to solve a small day-to-day puzzle, or if, for example, some in my equipment at my home is not working, when I try to find a solution to that and fix that, that brings me immense joy. Similarly, if a small kid is going through a math problem that they don't understand, if I'm able to help them understand, that brings me joy. So when I started looking at things from that perspective, then even making a script work would bring me joy. And then in the end result, which brings me the most amount of satisfaction, is when I'm able to communicate my work to a general
Mm.
audience. So although the work that goes behind the scenes is so monotonous on a day-to-day life, and but the you have to, like, if you want to continue in this field, you have to figure out what is that one point that you can hold on to, which is going to bring you a sense of joy on the days when you're doubting yourself, you're doubting the work, you're doubting your existence and doubting everything. So the something that brings me some assurance on those days is the number of people that I have been able to reach out with using physics or using astronomy. So I think having that as my superpower, I am happy to do all this background and back end work to present this nice, beautiful looking physics or my interpretation of my work to a general audience, which is then widely appreciated. So,
Mm.
yeah.
I think a part of it also becomes how well you are able to balance the surely the scientific and learning part, theoretical learning part, with also simultaneously hoping to realize, as you said, what particularly pushes you or motivates you from within intrinsically. Because
Mhm.
having one or the other, that too in the situation where you have the theory down, you've got perfect grades, so on and so forth, you cannot only you cannot do research solely based upon your on paper merit. It becomes hard. So, talking about the challenges, now there may be roadblocks that you hit, mental blockage, or maybe funding issues, publishing
Yeah.
processes, tediousness of the entire process, all of it. Like, talk about all of it.
Okay. So I come from Pune, which is a city in India, and Pune is considered to be education hotspot in India because it has all these different universities and institutes and so on. But although I grew up in Pune, the biggest exposure I had to physics outside of my school was something like a science center or something like an institute called Ayuka, which is the Inter-University Center for Astronomy and Astrophysics. And there's also a center called NCRA, which is a Center for Radio Astronomy. So these were the institutes that my father used to take me to just get some extra knowledge about science and some exposure about science. However, having said that, as a layman, as my parents were, who were, my father was an engineer, my mother was in customs and income tax. So they didn't know what the life of a astrophysicist or a scientist, or those days they would just call someone who's pursuing pure science, would look like. Well, today I can call myself an astrophysicist since I've done all this amount of work. But back in the day, I would just be like, oh, I want to pursue pure science. I did
Yeah.
not even have the confidence to say, I want to be a scientist or I want to be an astrophysicist. I want to be a physicist. I did not have that confidence.
Mm.
So I think the first challenge was for me to educate myself, to educate my parents, because the exposure and it's the physicist's faults too, because we don't make science easy for a layman to digest or for a layman to understand. Even when you look at pop science movies, I mean, even when you look at these talk shows, the language that's used, for my mother sitting in front of a TV, she'll be like, this is amazing, this is fascinating, but I don't think I could do that. I don't think I would understand that. Right? So then, for them who were not able to digest this idea of what a career in pure sciences would look like, it was very hard for me to make them understand why I wanted to go in this field, where I myself was in my late teenage, and then I was still figuring out what this field even meant. So that was the first biggest challenge. So once I overcame that challenge, the next challenge was to find the right mentor or the right peers. And unfortunately for me, I cannot say that I had a good mentor growing up who could push me in the right direction or guide me, you know what, if you want to do this, I think this would be a right direction. I had like 10 to 15 people collectively whose advice I would take and then just try and apply to this place. Okay, try and look into this place, explore this place, and so on. So the second challenge that I faced was not enough resources around me to for me to make the right choice or the right decision. I would write these random emails to even the director of Ayuka and NCRA, meet them for 15, 20 minutes, get whatever inputs I get. And then that's how I used to compile my resources in order to for me to make an informed decision. So the second challenge was the lack of resources. The third one was, now I am in Germany doing my master's in astrophysics, right? Once I went there, the kind of language they talked, not the language barrier as in English
Mm-hmm.
or German, it's the kind of science they talked. I started having this what's the syndrome called? There is this syndrome
Imposter,
that you
imposter
feel.
syndrome.
Imposter syndrome. Thank you.
Mm.
Yes. So I started feeling this imposter syndrome coming from such a small school and such a small city. And there you had people from different parts of the world. And when they talked science, I felt like I did not belong here. I just felt very short of myself. So the third challenge I had was to find that inner confidence or to even build that confidence and to try to overcome that imposter syndrome.
Mm.
So Then I realized, so what I would always focus on at that time, which I see a lot of people do, which in my opinion is not the best approach, is to talk to people for the purpose of networking. They feel that networking is going to land them the best job, or networking is going to, and going overboard with that. And I was also the same. I did the exact same thing, but it did not work out for me because I realized that that is only going to give me this external validation. Say, for example, I'm going to go meet this director and tell, oh, you know what? I just don't feel like I belong here. What are they going to say? You know what? You do. We all have started from there. I mean, they're going to give some affirmative words, right? But I don't think that helped me as much as going back to the grind work, going back to the coursework, doing all the mathematical problems by myself, reading as much as I can, and then attending a talk where I could understand the language of science, understand the language of physics that was going on. That was a moment when I felt like, okay, you know what? I have reached a level beyond what I was in my undergrad. And that sort of gave me that confidence or boost or a little bit of help with the imposter syndrome. That was the third challenge. The next challenge is when you start doing your PhD or your actual research, right? So, PhD in different countries, it looks differently, and the
Mm.
challenges in different countries are different. Since I've studied in India, Asia, India, which is in Asia, Germany, which is in Europe, and now United States, I have some awareness of what are the different challenges you face in like different education systems. But I'll specifically talk about the one in the US because that's where I was doing my PhD
Yeah.
from. So when you're doing your PhD, the system is built in such a way that for the first 2 years you take a bunch of coursework. You have
Mm.
to give this qualifying exam, and once you finish your qualifying exam and have an interview, then you are deemed to be a prospective PhD student. And in the US, this exam is really infamous to be one of the toughest exam, especially for the physics department, because you go through classical mechanics, quantum mechanics, mathematical physics, electromagnetism, all of it, and all this exam goes in 1 or 2 days.
Mm.
So going through all this grind, and then you start your research. But the first thing you have to find a guide. The guide should have some grant. If not, you have to do a teaching assistant job or some other part-time jobs to support yourself.
Yeah.
So that is the next challenge which generally all the PhDs face during their journeys in the US. But I was lucky enough to be able to exactly know which person I wanted to work with, and that person had funds. So I didn't have to do a part time teaching job in order to support myself. I could just focus all my energy on research. So once that challenge is crossed, the next thing that happened was compatibility issues. Are you compatible with your advisor that you have to be with for the next 3 years or 4 years or 5 years? Are you compatible with your collaborators for the next these many years? So that's the next challenge. I have been lucky to not have the worst advisor. Of course, we
Mm.
look at things differently. We look at science differently. We look at the purpose of life differently. But it was great. Like, she was great to me, and everything was very smooth and everything. But I've heard horror stories on how people have quit academia because of their advisor.
Mm.
So that's also a really big challenge when it comes to doing a PhD. And once you cross all of that and you end your PhD and start thinking about doing a postdoctoral research, independent research, that's when this funding bomb is dropped on you.
Mm.
That's when you're just independent and you're trying to write these proposals of 5 pages, 10 pages, and trying to convince the government, convince the people why they think your idea should be funded. So that is sort of one of the late end challenges that you would face. So, yes, so each of this has, I mean, I feel like I'm saying some sad sob story here, but that's the reality. There are
Yeah.
challenges in each and every path. And one of the biggest challenge which discourages people from choosing academia is a financial instability.
Certainly.
Because there are people who finish their PhDs in their late 29s until they are
Mm.
30,
Mm.
right?
Mm.
When you look at a person working in an engineering firm or an IT firm, by the time they are 30, they probably might already have some saved up money, and they might
Mm,
look at a different life. Whereas you are coming out of a student status.
mm,
So
mm.
your financial stability goes for a toss.
That's
And
true.
then you apply for postdocs, which could be for 1 year, 2 year, 3 years. You're done with that. Again, apply for another postdoc. Apply for faculty positions. So there is financial instability in each and every way. And the kind of tools that a researcher has in terms of software development or in terms of coding, if you would go to an industry, you would probably get paid twice of it. So that is another challenge that you have to overcome. What is my priority? Why am I still in this field? And unfortunately, in the last 3 years, I know 10 of my peers who have quit academia because of poor mental health.
Mm,
They went into depression, they had different sorts of mental health issues, and this is also not talked about in academia, especially. So, another challenge or a big challenge would be isolation, feeling like you don't belong somewhere, feeling like you don't have the right peer group, feeling like they don't understand you, you're struggling through this on your own. So one of the next challenges that I see that people normally face would be that of mental health issues. So yes, there are a bunch of challenges, but in the end, it's yeah. I hope we can come to the happy part later.
maybe one way to reach there is by you advising the young folks, the undergrads or maybe early researchers, into how exactly they can start that journey. One aspect being, maybe especially in today's day and age, when competition is, again, it's competitive. The competition is competitive, and you need to carve this your unique identity as a researcher way before you actually set foot across the door.
Yeah.
For programmers, for developers, software side of things, it's easy to create a proof of work or portfolio, something that you can show for to show your skills or represents your skills. For a field like astrophysics or physics in general, what exactly do you show as an undergrad as something that represents or displays your ability or skill set?
That's a very good question. It's a very important question because that is sort of a age where you're making the decision whether to go this way or that way. And I have faced the similar question and similar struggle. And I've been happy to talk to as many undergrads as possible. But one thing that I always, always, always tell them is to focus on their coursework, is to
Mm,
focus on their mathematical background and focus on their physics foundation. Because once you have all that, research is just application, and you're trying to think out of the box and you're trying to making different links between theories that are already existing. But what is absolutely essential is to have that strong solid foundation of physics and mathematics. So as a first year undergrad or even a second year undergrad, until they have to make that decision of writing the applications and everything, I would strongly recommend undergrads to just focus on their coursework and to ace it and excel it as much as possible. And once they feel like they are on that track, which I think should be the highest priority,
mm,
then they can start looking and talking to people on possible research opportunities. So it might be within your institute, it might be in a neighboring institute, or it might be a different institute where you can virtually collaborate with people. So today we have all these options because most of the research can be done virtually, and there are so many tools if you also want to share your mathematical or other kinds of work. And there are also a lot of schools like summer schools and winter schools for undergrads, which I think is an excellent exposure to how real research looks like. So, first thing is to just focus on your coursework, strengthen your foundations. And the second thing is to start exploring these ideas of research that you can at least do one research project. It does not have to be something completely novel, but it has to be something that is showing your future employer that you are thinking about research, you are serious about this, and you have intentions and the ability to think as a researcher.
mm,
That's the whole point, because whatever you do in your undergrad might be completely different from what you do in your PhD. So it doesn't matter that it has to always match. But what matters is if you have gone that extra length to get yourself some exposure in research. And the third most important thing is to reach out to people. Is do not be shy. You have to let go of your fear of rejection, let go of the fear of embarrassment, let go of the fear of hearing a no, and email people that you think are like minded and you think would be a good fit for you as a future employer or as a future advisor. 1 out of 10 might reply positively, but you just need one yes. Even if it's
true.
100, you just need one yes.
Mm,
So reach out to people, you have to be extremely polite and respectful, but be as shameless as you can in terms of trying to reach out. So that is another thing that these are top three things that I think if I were an undergrad, I would have
mm,
done more of these.
mm, mm. One other thing, especially as we move forward, the blurring of lines, or maybe merging of lines of different fields into these interdisciplinary bubbles of sorts, where remotely you can arguably apply or utilize any facet of any pure field into a subset of another and make something that is of potency or value to either a particular group of people, humanity at large, whatever. You can find your user base, sort of. In such a case, how does someone, okay, I'm an undergrad, acing my grades, straight A student, fine, have got that covered. I also started working. I know that, okay, I'm interested in physics, maybe interested in astrophysics, done. With so much bombardment of so many different niches out there which are bleeding into each other, how exactly do I a be able to fathom to whatever degree possible in terms of what all is possible? Because even if I want to know that, okay, what is something that is suitable for me, what is a topic, a niche topic or area of interest that will be of interest to me, I need to at least know about what areas of interest, potential areas of interest, are out there. So firstly, how do you go out and actually know about what all things that there are? Secondly, how do you keep up with the requirements or the prerequisites needed? So I did physics for my undergrad. I've got that solid base in physics and mathematics. But let's say we'll come to the computational part of this. But let's say suddenly I realize that, okay, coding and programming have become a sort of precursor to more or less everything that we do now, because I need to know how to play with data. How do I then take up this new skill stack that I was not in touch with at all, integrate that into my working and flow of things that I'm able to easily do? So, two things. Firstly, again, explore, know what all out there is, what potential things are out there. Secondly, how do I build these prerequisite skills that are needed for these interdisciplinary terms? And third, finally, how do I realize that, okay, which niche subdomain is something that I'm interested towards?
Okay, let's go one by one. So, first thing is how do you get the exposure? How do you know what's out there? And the way I did it was just start the random Google search, top 10 institutes for gravitational physics in Europe, and then start from each institute. What is this institute doing? They might have 10 tabs. Go through
Mm.
these 10 tabs. What are the research they are doing? Who are the people that are working there? What are some of their research highlights in the news these days? Okay, go to the second institute. Go over what all they are doing. So that was my source of information. I generally believe and I rely less on what people tell me. And I like to go do the groundwork myself and read the information myself because information is updated each and every day.
Mm.
Whatever I am telling you about Germany, for example, was the information I had 6, 7 years before.
True.
So I might tell you something which may not be true today. So, but that gives you a direction. And it is just to give you a direction on where you can go and where you can get the larger information or the more accurate information. So, one thing is that all these universities have very well developed web pages. All the information that you want is there, is right there. It could be the prerequisites, it could be what kind of research is being done there, it could be any faculties that are working there. All this information is out on the web.
Mm.
And all of them have an email ID where you have a department ambassador, an institute ambassador, a university ambassador. And they are students to staff to faculty and everyone who are generally very, and their job is to help prospective students or prospective joinees to know what is going on in their institute. So the first thing is to just go over all these different institutes and to research out what is out there and what could be your potential area of interest. Well, the second thing is when you talk about interdisciplinary science, as you said, everything today is interdiscipline. You cannot do physics without having some computational background. You cannot do physics without having some mathematical background. So it's all going to be interconnected, and it's the same for biology, chemistry, etc. So the way that I think is I like to start with the problem of my interest, a very defined problem of my interest. For example, the problem that excites me the most is gravity. What is gravity? And that when I so that has already narrowed down a lot for me because physics is so vast. There is condensed matter physics, there is nuclear physics, there is quantum physics, astrophysics, gravitational physics. You can go on and on and
Mm.
on.
Mm.
So just by narrowing down that one question that really interests you can already start giving you a direction. Once you have that question, then you can start looking in that direction. Which institutes are good for gravitational physics? Which institutes are good for condensed matter physics? And when you go in there, they would have classified the research as observational, theoretical, numerical. Then you ask yourself, do you see yourself every day going to the telescope site, working with the instruments, and looking at the sky? Answer is yes, that's a tick. Do you see yourself writing codes, debugging the scripts, working with large data, and doing some statistical analysis? Yes or no? That's another tick. Do you see yourself confined in a space where you're indoors rather than where you're outdoors on site working with instruments? So when you start brainstorming with yourself with these questions, you naturally start sort of getting answers of what exactly is the path that you want to follow. And that path, and that is, I think, most important thing for me because I've also heard stories where people are like, I don't know what else to do. I just joined this. It worked out. And I after this, okay, this opportunity walked to me. I tried it, it's worked out. And they're super happy with it. But for me, everything has been a extremely conscious choice and a conscious decision of what is lining up with my interests, what is lining up with my values, what is lining up with my source of joy.
Mm.
And the third thing is when you talk about was it more like, I think I forgot your third question. Was it how do you do the interdisciplinary science? Or
You sort of
I think I
answered
lost
it.
track.
It was how do you then zero
Yeah.
down upon what exactly your particular
Okay.
unique niche is?
Okay, yes. So that sort of, so if you're just making this list of things
Mm.
along with yourself of what is works for you, what does not work for you, That was my approach to how I got here today. And even though I'm here today, I still have so many choices to make, even for the next year. My current job would be ending soon, so I need to apply for new jobs. So then when I'm applying, do I want to stick into this niche of gravitational physics? Do I want to explore more into, say, solar system physics or supernovae physics, or etc., for example? So all of these questions have to, like, you have to start brainstorming with yourself, and all of that shows up in your application.
Mm.
Because you could today use ChatGPT to write an excellent cover letter that
Mm.
would be very well written, with great English, with great grammar and everything. But how much of that has come truly within you? When you start brainstorming this with yourself and really understand yourself, that translates in your cover letters, and it should or would connect with one of the employers from out there. So, yeah.
Ideally, the one that's most suited for you. But okay, maybe coming back to the simulation and modeling aspect a little bit more. How exactly do astrophysicists attempt at computing the cosmos?
Well, there are, when you talk about astronomy or astrophysics in general, it's a vast field. It's a really, really vast field. There are people who specifically study supernovae. There are people who specifically study neutron stars. There are people who specifically study solar systems. And each of them have a different, not a different way, they sort of, I mean, they're trying to solve similar problems, but they have different questions that they're trying to answer. They talk about big data. Today, there is a lot of data for all the kind of questions that are trying to ask
Mm.
within astronomy. So when you talked, since you mentioned the word cosmos, let me start with cosmology. So you talk about cosmology, you're talking about the large scale objects. That is, you don't worry about what is happening at the star level.
Mm.
You're asking questions what is happening at a group cluster of stars levels, or even less, what is happening on a larger cluster of galaxies level and out there until however back in time you can go to. You talk about these questions. The next question is, what is your data? Right? What is your data to be able to answer these questions? So your data could be all these projects and satellites which are going around photographing, these telescopes that are going around and photographing different aspects of the universe in different electromagnetic regimes.
Mm.
And that is the data that you get. So for example, you have a data that is looking specifically for not just say galaxies. So the job of the telescope is to spot galaxies and to record when it finds a galaxy. So then you have a catalog of all galaxies, and that's your data. And then you can go over this catalog of galaxies and then analyze what color spectrum of galaxies I'm looking at, what length of galaxies I'm looking at, what is the distance within the galaxies I'm looking at. And you start doing some statistical analysis.
Mm.
So similarly, you can ask about exoplanets, right? So there could be a specific project that only focuses on looking at exoplanets. Which of these planets can be classified as exoplanets and why? So that will be your data. The question is, do I see some transit around this planet, like a moon transit around this planet or so on? So if there's a yes, that will be your data point. So the point is that different questions that are trying to answer have different data set, have
Mm.
different catalogs. And then you use very similar theoretical approaches like stochastic sampling, Monte Carlo sampling,
Mm.
Gaussian, fitting a Gaussian, and just the statistical techniques are still very similar across what's used. But the question that you're answering using the statistical tools varies with each of the field.
Picking from where we left off at the very beginning, gravitational waves.
My favorite. Yeah. So So, the first time when I came across gravitational waves was when I volunteered for a public outreach program, which was in collaboration with Ferguson College, where I did my undergrad from Ferguson College and Ayuka. So that was a collaboration, and Ayuka wanted student volunteers to do public outreach and to spread this idea of gravitational waves. It was so new, and it was just that year that they had detected the first gravitational waves. So when I started looking into the idea of gravitational waves, it was just so fascinating and something that I had not really thought of, that it was just like an immediate love at first read, where I was like, okay, this is exactly what I want to do. So, talk about gravitational waves, it is still a wave. The name itself suggests it is still a wave and it has something to do with gravity.
mm,
And the way we understand gravitational waves is again going back to the framework that Einstein has come up with, which is this framework of space and time. So now I talked about there being a huge, massive object like the Earth, and there being a smaller object like the Moon, where the curvature in this fabric is causing this force of gravity towards the larger object. Now imagine instead of there being one Earth, there are two Earths and they are going around each other, or there is some sort of acceleration happening in this mesh. That means the entire mesh is going to have some sort of disturbance and some sort of vibration. That means this vibration, and imagine this mesh is infinitely long,
mm,
right? That means if there is some acceleration or some distortion that happening here, can be felt by someone who's sitting there
mm,
just by the traveling of disturbance, just how you would have the waves on a sea, on an ocean. So that is what we term as gravitational waves. When you have gravitating bodies which have these huge accelerations, they distort this mesh of space and time. This distortion moves across space and time and can be detected by a far away observer. And the
mm,
same way, how this disturbance is in the space time, the same disturbance can go until them, and they can have read off this disturbance at a later point. And that's exactly how we detect these gravitational waves, which is like disturbance that is traveling across millions of kilometers or light years.
mm. Apart from, okay, it took us almost around or a little more than a century for us to detect gravitational waves after Einstein postulated this entire framework per
Right.
se. Apart from only the technological advancement aspect, would you attribute it to maybe some sort of theoretical advancement right now, or thereof lacking in the past? If yes, what is it
So,
particularly?
yes, so Einstein already had all the theory ready, but the question is, was it believable? Was there enough truth? Like, how do you know if there's enough truth to it to invest millions of dollars to build a detector to detect it? So, what actually took time was for people to get convinced that this is true. We
Mm,
can detect gravitational waves, we can indeed detect gravitational waves, and then translating that as a grant to convince the government that this is a project that is going to work and this is a project that will be revolutionary, etc., and the government sanctioning it and then sort of building the technology. So that was what was going on for that 1 century.
mm, mm. Taking it a step further to where you initially told us that it all breaks down, black holes. What particularly right now is the most call it the bleeding edge understanding of ours in regard to the interplay between how these black holes stay and this entire nature of gravitational waves, they interplay with the larger cosmos.
Yeah. So, what we are out there to achieve in the next decade is to cover the black hole population of the observable universe. So that's the larger aim. So there are multiple detectors which are being sanctioned and which are under construction. And once they start running, and once we're able to record data or gravitational waves from them, then within the next decade, optimistically, we would be we would have a scan of the observable universe and have the information of the entire or 99% of the black hole population of the universe. So that's the aim
Mm.
that we have. So that sort of is itself like mapping the cosmos, right? Because you're getting this information about these black holes from different points of time and space. So that is one way we aim to map the cosmos. So in terms of just black holes, talking in terms of just black holes. So yeah.
What about to what level of accuracy are we able to? Okay, the last thing that maybe in general common folks will be worst with is how with black holes, apart from the singularity and the light not traveling past a certain point, entire thing, the basic structure of it, apart from that, in the recent years, after all the work that Stephen Hawking did, after all of it, post all that understanding, currently what is the most advanced know-how of the nature of black holes, and thus gravity and gravitational waves by correlation?
I think that a huge advancement that we had was the first image of black hole that we
Yes.
recently had. So that did not have anything to do with gravitational waves. That
Mm-hmm.
was by a different project, a different telescope. But the most advanced, I think, when you talk about a single black hole, I think that would be the most advanced information we have from a single black hole. What we gravitational wave astrophysicists do is not look at a single black hole. Our data point is that of a binary black hole. And we look at the dynamics of the binary black hole. What happens when there are two black holes in the vicinity of each other? How are the dynamics changing? How is the effect of gravity changing? And so on and so forth. So, with this high data that we're getting in of this binary black hole, one thing we have able to verify is Hawking's area law theorem. Another thing that we have been able to do is when you look at um, the space with electromagnetic telescopes, the scientists had made a deduction that black holes can only exist between a certain mass range. They were not being able to find mass ranges within a certain mass range. But using gravitational waves, which does not need any sort of radiation to come from a black hole, it does not rely on light not escaping from a black hole, it does not rely on the Hawking radiation. It only relies on this gravitational distortion that these black holes are causing. And that has given us a new set of population filling this gap of mass, just refuting this long-standing um, claim that black holes can only exist from this range to this range. So it has widened our, because different sizes of black holes, you need different kinds of physics to understand how they come to that size. Because as we know, black hole is a death of a star, right? You need to have a certain size of a star or a certain supernova explosion or a certain event that has caused a black hole of a certain mass and a certain size. So if we always believed that this set of masses never existed, we would never think of the possibility of the physics that might have led to black holes of that mass.
Mm.
So now that we have this wide range of masses and distances of black holes, that gives us more food for thought as to what are the processes that should have led to these black holes. So these two, I would say, would be the most advanced ones.
In general, how do you see the future of astrophysics being in the rest of the century? Now it's a long time to postulate for,
Yeah.
but still maybe to whatever degree of closest degree of freedom you'd want to estimate it to, what in your opinion it all would be.
Well, I think one of the most interesting things that is going to happen is, so currently we're detecting gravitational waves from ground based telescopes.
Hmm.
And soon, hopefully soon, in the next decade or so, we would have a space based telescope. And that is going to completely change and revolutionize the kind of information that we are getting.
Hmm.
And there are also projects to have gravitational wave detectors on the moon. So all of these are like leveled up versions of what we see on Earth because we have been so successful in getting this data from the detectors on the limited space that Earth has that the governments are now happy to expand the projects to this level of space and even on the moon. So just from the gravitational wave standpoint, I think this is going to give us a lot of information if Einstein's theory is the most fundamental theory of
Hmm.
gravity. If there is a larger theory that is existing, because we're going to have so much data that we're going to see a different all sorts of observations, and we can look at the predictions of this long list of theories that we have had and say, you know what, we've observed this, and to this accuracy we don't think this theory is correct, or to this accuracy we don't think this theory is wrong. So we can put these constraints or limits on these, because I feel there has been a large gap between the development of theory and the development of observation of
Yeah.
technology. So theory is far ahead than
Hmm.
what we have from technology.
Hmm.
So
Hmm.
with this detectors coming up and with this data, I think we in the next century we can get closer to that and probably have some sort of answers to, or even get closer to the theory of everything. So I don't see that being a completely impossible situation. So if you talk about the next 100 years.
I mean, with that scenario hopefully playing out, what would be your advice to the new and upcoming generation of physicists, astrophysicists, and people who will be in general interacting with the developments of gravitational waves?
So gravitational wave development, I mean, we have a detector coming up in India, in Maharashtra as well. So India is also very involved in this entire world
Hmm. Hmm.
collaboration of gravitational wave science. And this is bringing up a lot of opportunities for engineers, for physicists, for mathematicians, for computer scientists. So it's going to bring up a lot of opportunities for everyone. So I think the first thing is to get the right exposure as to what is expected of you. I mean, the question is, do you want to take this job up? If this job is right for you. So, first, just get a lot of exposure by talking to people or just browsing through the sites and
Hmm.
understanding what is exactly required. Because I wouldn't want people to join something and regret 2 years down the line, giving a 5 year commitment and saying, oh my
True.
God, my life is miserable and I don't want to do this. So, always be extremely aware before jumping into something, especially if it's a long time commitment.
Hmm.
And second thing is not to doubt yourself.
Hmm.
If you not to doubt your inner voice or your gut feeling, which is what I have learned, is that if you, even though people around you don't feel like this is a right fit for you, this is not the right direction for you, or this is you're dreaming and you're just being very far reaching, just don't doubt that inner voice if that says, hey, you know what, I have got a good shot at this. Just give it a shot. You never know, it might work out. I mean, we often hear about these things when you talk about people wanting to be actors or people wanting to be in the industry of glamour and fashion and everything. That, oh, I always dreamt of being this, but I did not have enough resources and blah blah. We never talk about it in terms of science because it's considered to be such a dull and gray field.
Yeah.
But it's the same philosophy that applies here. So there are people who are extremely successful with maybe it not monetarily successful, but maybe successful in terms of their publishings, in terms of their work satisfaction, in terms of their purpose being satisfied and everything. But I think is always to listen to your inner voice and to be active in searching for new information, active in brainstorming with yourself, active in figuring out if this is the right thing for you. So, yeah.
I think one of the key developments is also going to be the more ardent and robust involvement of the private players in private partnerships to come into play, which will in general elevate the again this I'd say even the investment ratio that currently is only through governments and research grants and so on and so forth. But then just one particular maybe point of clarity then in that regard from you, to study something that is of such immense scale and requires such levels of precision and maintenance in regard to the equipments and apparatus used, how exactly would you see the new upcoming research setups may be in regard to academic labs or otherwise industry ventures to be of purpose or value in the wider study as compared to the already established behemoths like Virgo or LIGO, so on and so forth? Like how exactly will that interplay be?
So that's a very good direction of thinking, especially for us who could be the next generation of scientists and so on. I
Mm.
think it's a great um, direction to even think and ask ourselves about these things. I think there is a huge gap between the education system and what is being applied at research and technology. Even you think about a school education system, right? I don't think we have it for like a middle class school. I mean, you can talk about international boards and really advanced schools and keeping them aside. Just like a regular middle class or upper middle class school, they don't tell you how to think. They teach you how to get great grades and how to, and that is sort of their idea of achievement and idea of success, but they won't encourage you to how to think. I
Mm.
mean, you're often punished to be thinking outside of the box or asking questions outside of the box. So you talk about the education system, there has to be a huge change in terms of the education system. That I often have this complaint to my parents that if you would have put me to a better school or if you would have had like a better education, I would have reached here quicker or I would have done this better and so on. But I truly feel that this has to start stemming from schools, because when you observe these little kids, they have so much curiosity and such bizarre ideas. They
Mm.
enter the school, and once until by the time they come to the 10th grade, all they think about is how am I going to get 95, 96%, and how am I going to get the cutoff mark to go to the
Mm.
next. I mean, that's how the education system is set up. So we cannot complain that unless we are going to go against system, we have to be a part of the system. But if a bunch of people who think like who can think out of the norm or who can have a non-traditional thinking, if like a bunch of us come together and we can have some sort of maybe a consultancy or maybe a teacher's training or maybe like a school training. So these are some things that we can provide to the schools in order to help them teach the students the right way or to prepare them for these massive growth in technology, which is not at par with what happens in schools. Yeah.
Yeah, I think yes, I agree. A big part needs to be about, well, teaching how to firstly embrace the non-conformity, and secondly find ways or help the kids in finding ways to rather discover their own unique non-conformity that they may be able to put use to.
Yeah, definitely.
And maybe then, okay, sort of the final potent question that I think people will really benefit from, to tie it all up into a singular cohesive message that you'd want to leave everyone with, what exactly would be your word to humanity at large?
Um, I think it would be live and let live.
Hmm.
And be, um, I think it would be unabashedly yourself, but not at the cost of somebody else's peace or happiness. You do whatever you want to do without being unkind to someone else, without causing pain to someone else. But yeah, this would be the message. Yeah. I've never really thought about it, but I think these two would be the top two things that I would tell to humanity.
I'd say spot on. Really, really spot on. But yes, Dr. Purnima Narayanan, thank you so very much for having this conversation.
Thank you.
And I'm particularly sure that people will be enjoying this for a variety of reasons, from being able to get to know about again the academic and theoretical side of the subject matter, to getting to know some pragmatic insights and anecdotes that they may be just able to imbibe in their own workflows, and get a perspective in regard to the past, present, and the future of the direction of R&D in
Mhm.
general in this subject matter.
Mhm.
So thank you so very much.
Mhm. No, thank you. Thanks a lot for having me, and thank you for these wonderful questions. I absolutely enjoyed having this conversation with you, and kudos to your determination and for this initiative. This is great.